Yeah, I welcome Dr. Rajeev sir for today's presentation. So he'll be delivering a talk on basic, so very fundamentals of atmospheric boundary layer and related areas. He's a very known person in this area, especially even in national, even in this area, he's throughout the globe actually is known for his work. Especially, he has many publications in the related areas like boundary layer convection and related areas. And he was a distinguished scientist in SPL, Space Physics Laboratory, VSSC, and he was also previous director of Space Physics Laboratory in VSSC. So, sir, please kindly deliver.
Thank you, Dr. Krishnan. I have made my talk in such a way that it is not too advanced. At the same time, it covers some of the most recent research areas with potential applications even today, applications as well as research potential. Today's talk is on introduction to atmospheric boundary layer. Hope those in the online can hear and see the presentations. Can you respond? Anybody? I think we'll proceed. Yeah. So thank you for this opportunity for interacting with you. We will start with. Before going to the atmospheric boundary layer, I would like to give a brief introduction to the atmosphere, which will not be very exhaustive. It will be very primitive, but certain things need to be covered. I will go faster because here you already are masters in these things. You basically know that the atmospheric composition is nitrogen 78%, oxygen 21%. They are the major constituents, and argon is around 1% approximately. And there are several minor constituents like water vapor, carbon dioxide, ozone, chlorofluorocarbons, as well as you cannot call that as a species. I mean, atmospheric molecule, but rather constituent. You can consider aerosols also. The importance of these minor constituents is that they are the ones who modulate the climate of the Earth atmosphere system. They play a very pivotal role, including greenhouse effect or the interaction with the clouds and things like that. Mean molecular weight, this we have to keep in mind, mean molecular weight of dry air. When I say dry air, water vapor, minor constituents are 0. Then your mean molecular weight, minor constituents, especially water vapor, is 0, because other constituents are very, very small. It doesn't affect much, but water vapor affects the mean molecular weight because it's, it can be as large as 0.5%. It can be very low as 0.001%. It is a highly variable species. So the mean molecular weight of dry air, when we say dry air, devoid of water vapor, that is what dry air is. So that is 28.96 gram per mole. But when you add water vapor into it, mean molecular weight comes down because water is less molecular weight compared to the air, because oxygen 32 and 28, whereas water vapor is only 18. So when you add up, your mean molecular weight comes down, but it doesn't come down drastically. Minimum maybe of the order of 28 maybe 85 of that value. We may think it is not a big deal, but it's a very big deal, especially even for rocket launchings. They consider these things because to consider track, it becomes very important because we find the scale height, and scale height depends on mean molecular weight, and we derive parameters from that. Then that small number, it becomes very important. So it's very important that we realize that 28.96 is for dry air, Whereas when moisture is added and if moisture is very large, it will be proportionately coming down depending on that mean molecular weight, 18, what is the percentage that you are putting in. So it can be as low as 28 point, probably 8, 8, 5 kind of. Of course, it will not come down much below that. Pressure decreases exponentially with height. You know that. And we say that pressure is, say, approximately 1000 hectopascal at the surface, 13.5 hectopascal is the mean pressure. And at around 5 kilometer, pressure is close to 500 hectopascal, which means 50% of the atmosphere is below 5 kilometer and 50% is above. When you come to around 18, 19 kilometer, your pressure becomes very low. So correspondingly, the atmosphere, part of the atmosphere becomes very, very small above that. And this is another very important thing. So the bulk of the atmosphere is below around maybe around 10 kilometer or 90% of that, because where the 100 hectopascal pressure comes, it is close to around 13 kilometers. So at that place, you have only 10% of the atmosphere above, remaining 90% is below. One interesting thing here is you can do a calculation yourself. You take surface area of Earth and you find out how much is the pressure. Pressure is nothing but the force acting on unit area, which you can convert to mass. You take acceleration due to gravity. Pressure can be converted to mass. And that mass, if you take, and the total area of the Earth, 4 pi r square. Atmosphere mass is close to 5 into 10 power 18 kilograms. There can be small changes here in the numerical calculations. It is not that atmospheric mass changes drastically, but that in numerical calculations there can be some small changes, which is approximately 10 power 6 times lower than the mass of the Earth, because Earth is solid. It is much. The pressure at the surface is around 10 power 5 Pascal. That's why we say 1000 hectopascal. If I take the amount of air that is required, mass of air that is required to produce this 10 power 5 pressure, that is 1000 Pascal, that is 10 power 5 Pascal, that is 10 power 5 Newton per meter square. It works out to be you require around 10,200 kilogram of air per meter square. Now I take a small child standing vertical. Like instead of child, you yourself can be. Approximate size, I take 20 centimeter by 20 centimeter. The area is 0.04 meter square. If I multiply this, I get around 400 kilogram of air above each one of us. And I don't think we will be able to carry this 400 kilogram of air in our head. There is something else happening. So, what is really happening? Pressure decreases exponentially with height, because first thing is every molecule, every species want to be in minimum potential energy state. So all of them want to come to the surface or even go interior, but if they cannot go interior, they will come up to the surface. They want to be at the surface where potential energy can be minimum. But at the same time, for a fluid, there is another force that is acting, that is pressure gradient force. That is, it wants to go from a high pressure to a low pressure. So in the atmosphere, these two forces counteract. You have high pressure here, low pressure up in the atmosphere. So the species want to go from high pressure to low pressure. This is called the pressure gradient force. Opposite happens for the fellow who is standing at any altitude. They want to come down. That's called gravity. So these two things matches. Pressure gradient force becomes equal to the gravitational force. But only thing is these forces are in opposite direction, because pressure gradient force want to go it up and the gravity want to bring it down. If I equate them, we will say dP by dz is equal to minus rho g, assuming unit mass. Unit mass. So this is called a hydrostatic equation, and this is one of the most fundamental equations in atmospheric science. And you can derive the altitude variation of pressure simply from this equation. That's why I told you, when you are finally converting, there is only one term that will be coming later on. That's called a scale height. If you want to derive pressure at an altitude, that's called pressure altitude. There, your mean molecular weight has to be very much, otherwise it will be problem. That is the importance of the mean molecular weight there. And you see, we are living in this kind of environment where this kind of pressure we are able to tolerate. Suppose we are going up, it is not just the lack of oxygen alone. You will start bleeding because external pressure is very low. So we have to have a conducive environment where the pressure is somewhat maintained, not just oxygen. The second aspect is if you go deeper in waters, for example, diving into the ocean, you cannot go beyond a few tens of meters. It will be a problem. So our body is conditioned for living in this kind of an environment. Of course, it can vary a little bit. For example, hilly terrain, people live up to say 4 kilometer altitude. People live 600 hectopascal. They are accustomed to that. Similar is the case of divers. They can go maybe a few tens of meters now, maybe a little bit more. Additionally, if you want to do anything, you require guardians to protect your pressure. That's why we do. Anyway, we will not dwell much into those things. But these things have physical relevance, and all the things which we study should have been directly correlated with what we are actually observing, feeling. Then it becomes very interesting. Atmospheric science becomes very interesting. Earth gets almost full energy from the sun. There is a small energy that comes outside the sun, from outside the sun. That is, one is stellar energy, but that is very minimal. Second is within the earth you have the geothermal energy. But if you take the fraction of geothermal energy or stellar energy to the solar energy, it is more or less negligible. So we always consider sun drives the whole atmosphere system. And you see that in space, this is taken from moon. It's called Earthrise. It is a body that is standing in space, and it is in equilibrium. Okay, everything which happens inside has to be internally adjusted, and total energy is given. That's all. Whereas we see that the atmosphere becomes so complicated, weather becomes very complicated, so many issues take place. But everything has to be conserved within that. And outside, we will come to that in a later time, that the energy that is coming in is equal to the energy that is going out. There's no change. But internal adjustment takes place when we are trying to perturb the system. We'll come to that. This is a figure which is quite serious. It may look a little bit complicated, but it is not that complicated. This is by Trenberth et al. 2009. This tells us what is the mean energy budget of the Earth atmosphere system. How much is the energy that is coming in from the sun? How much is the energy that is redistributed within the atmosphere? And how much is the energy that is going back? This gives the complete picture about whatever dynamics taking place in the Earth atmosphere system and climate change and factors, all those things, including relevance of boundary layer. So I would like to start with, solar radiation. I told you that you have 1368 watt per meter square, but that is normal to the Earth. But Earth has a night side, evening side, and polar side. So if you take Earth as a point object, don't take all the things. Earth as a point object, and take the mean picture, so that day, night, all those things are averaged out. Then the total amount of radiation that is coming to the surface, diagonally averaged, Earth as a point, is 341 watt per meter square. Okay, so exactly speaking, 341.3 watt per meter square. Instead of doing this for ease of business, let us take that as 100 units. So what is the energy coming from the sun is 100 units, but that 100 unit is actually 341.3 watt per meter square if somebody want to convert in terms of watt per meter square. Out of that, how much is coming to the surface? Only 47. The remaining is not coming. What happens is, out of the 100 watt per meter square that is coming in, you have 30 units reflected back to the space in the short wave domain. This 100 unit is coming in the solar spectrum. That is, we say short wave domain. Short wave domain means visible, infrared. Short wave, infrared together. That is short wave. So 30% is going back. That is called Earth's albedo. In fact, you are able to see the moon during a new moon day. You can see the full disk of the moon. You will see a bright arc portion and a very light full disk. That disk has come from the reflected radiation from Earth. Like in Earth, we have moonlit surface. a moon has earthlit surface. So that earthlit come from this 30%. In fact, historically, for the first time, the amount of radiation that is going back from Earth in the short wave domain was calculated based on by the astronomers based on, and with the satellites today, we find that yes, the number is 30%. Question is, what is this 30% constitute? Of this 30%, 23% is coming from the atmosphere and 7% is reflected from the surface. Each surface will reflect at its own value. Some surface may be highly reflecting, like icy surface. For example, glaciers will be highly reflecting. Ocean may be less reflecting, except in the Glen region, ocean reflectance is very low. So average value is around 7%. It is not that every surface will be reflecting at 7%. Average for the Earth is 7%. That is reflected from the Earth, and around 23 from the atmosphere. From the atmosphere, what are the constituents? Rayleigh atmosphere, atmosphere is blue. That means the radiation that was coming was scattered and it was wavelength dependent, all those kind of things. That is 6. And the remaining 17% come from clouds. So out of the 30 unit that is going back to space, majority come from clouds. The atmosphere and Earth together constitute less than what is constituted by clouds. That is the importance of clouds. That will come later. For the time being, see, 30% is reflected back. 47% has reached the surface. 7% are reflected from the surface. Now you see on the right side, the right side you have 30 is going back, but in the terrestrial IR radiation. That is IR radiation from around 4 micrometer to around 40 micrometer. Because Earth is emitting, you and me emit, any black body, any body will be emitting sigma t power 4. So Earth will be emitting, at surface will be emitting, clouds will be emitting, atmosphere will be emitting. The total amount that is going back is 70. We call it as percentage because 100 unit is the solar radiation that is coming. So you see at the top of atmosphere, 100 is equal to 30 plus 70. So top of atmosphere is balanced. Now you see the earlier figure which we are showing, Earth as an isolated thing. So at the top of atmosphere, Earth atmosphere system as a single entity, it is balanced. The remaining is taking place within the atmosphere and the Earth. Now let us see what is happening. Out of the 100 unit that was coming in, we told that 23 is reflected by the atmosphere, 7 is reflected by the surface, 47 reached the surface, and 23% was absorbed in the atmosphere. There is a small fraction of the solar radiation that is absorbed in the atmosphere. So for example, water vapor absorbs, water absorbs, even ocean, the water clouds absorb short-wave radiation. You have ozone and species like that which absorb. So total amount of radiation that is absorbed by the Earth is 27%. Solar radiation. Out of that 23, 19 is by atmosphere and 4 is by clouds. Now you just see the bottom side of the right part. The surface is emitting 116 units, which is much larger than what it has received. It has received only 47 unit, but it is emitting 116 units. How is it possible? It's possible because this 116 that is getting emitted goes to the atmosphere. Atmosphere absorbs most of them. That is carbon dioxide, water vapor, greenhouse gases. They absorb the IR radiation and they re-emit in turn. While re-emitting, part of it goes to space, part of it come back to the surface. And you see 116 it is emitted, the estimate is around 98%, 98 units come back, not 98%. If I take solar radiation is 100, then 98 units come back. 116 is emitted, 98 is coming back. And this 116 that was emitted, 104 is absorbed at the atmosphere by clouds and other greenhouse gases. And without interacting with the atmosphere, around 12 unit goes to space. That doesn't interact with the atmosphere, it straight away goes to space. Around 58 is going back to space after this atmosphere absorbs and it re-emits. Re-emitted fraction going back to space is from the atmosphere is 58. What is emitted to the surface is 98. So you have an atmospheric layer, going back is 58, coming inside is 98. Okay. You have to have an understanding on why this difference. It should have been equal. It is not equal. The reason being the atmospheric temperature decreases with the height. Okay. So in the lower portion temperature is warmer, upper portion temperature is lower. So result is what is going back to space by the black body if you take as a single slab. But the slab temperature not remaining the same. Going back will be only 58, but coming inside will be much larger. So now the net result you see, what is the effect? If I add up the numbers, as I told, at the 100 that is coming in, 30 is going back as reflected radiation, 70 is going back as emitted radiation, top of atmosphere radiation is balanced. At the surface, 47 has been absorbed in the short wave, 116 has been emitted, and 98 has come back in the radiation. Now you see what is the gain? 47 plus 98. 116 is emitted. If I subtract all these numbers, I get 29. And 29 is plus because 98 plus 47 minus 116. It becomes plus 29. I have an excess of radiation at the surface now. Look what is happening in the atmosphere. Atmosphere 23 is absorbed in the short wave domain, 104 is absorbed in the long wave domain, and 98 is emitted back to the thing, and 58 is going back to space. If I sum up all these things, gain and loss, I find that around 29 unit there is a deficit. Means atmosphere emits more than what it receives. Surface emits less than what it receives. As far as radiation budget is concerned, not possible. It cannot sustain because surface will keep on becoming warmer. Atmosphere will keep on becoming cooler because it is completely lost. There comes the magic. What I told so far is radiation budget. Energy is not radiation. Energy comes not only from radiation, it comes also from mechanical processes. Mechanical processes include convection. For example, you have ocean bodies or water bodies to say. Water get evaporated. Latent heat of water is removed from the surface now. Goes to the atmosphere, condenses, it liberates latent heat. So you see that excess of energy that was there at the surface was taken up by the latent heating, and latent heating now atmosphere is carrying it. There are mechanical processes like convection and things like that. It carries it, otherwise it will not get condensed. And at the place where it condensed, remember this, at the place where it is condensed only, it will liberate the latent heat. It will not liberate when it is going up. For example, clouds occur at 1 kilometer, say. It will not liberate at 100, 500 meter. It will not liberate at 200 meter. So there, this energy is not mattering. So latent heat flux comes, taking from the surface and dumping in the cloud where the clouds are formed. There's one more thing happens. Even without clouds, you have a hot surface. Air is rising from a hot surface, and it is going to a colder area. It will carry heat with it. That is called a sensible heat flux. It's something like you are going near a fire, and if you go near a fire, you will get more radiation, more heat. Remember, more heat. There will be more radiation also. That part we do not consider. If you go near a fire, you will also get more radiation. The radiative heating also will be there, but there is significant amount of heating that will be coming because of the hot air coming to you. This hot air coming to you is called sensible heat flux. So surface is hotter, atmosphere is colder, air rises, heat is taken from here, that is sensible heat flux, and continuously dumped in the atmosphere. It is not that it is liberated at some particular altitude. Each step it liberates. How it liberates? Because it has to do work to go up. So while going up, it has to spend the energy. So that energy is spent at each step. So there's a fundamental difference. You have the surface latent heat flux, surface sensible heat flux. They dump the energy. Latent heat flux is dumped only at the place where condensation occurs. Sensible heat flux is continuously getting dumped in the atmosphere up to which this dry air goes, or the air goes. This is a fundamental difference. There is one more thing. Latent heat taken from here will almost in majority of cases, it will not be dumped above you. It will be carried very long distance and then cloud may be formed somewhere else. For example, water that is getting evaporated in the Arabian Sea during the monsoon season comes to India and so what latent heat was taken from the surface at the Arabian Sea and that too even Central Arabian Sea or Western Arabian Sea or even South Indian Ocean, and they get dumped in the Indian region. So you don't have an one-dimensional atmosphere. You need to have a pakka three-dimensional atmosphere if you want to handle this. Okay, so this is a very simplistic picture, highly simplistic picture, but at the same time, it gives you far more insight than any figure that it has been produced. And what this Strandberg produced it for Earth, and it is getting revised every now and then. Why it is getting revised? You are perturbing it because 116 is emitted, 104 is absorbed by the atmosphere by carbon dioxide and species like that. You are emitting more now. So carbon dioxide greenhouse effect changes. 104 will become some other number later. Or previously it would have been a lesser number. You are perturbing it. Now while coming back, it will not be 98 because 104 is absorbed means it will be equally emitted also. So more amount of radiation will come back. Surface temperature will change. One side. Second side, you have, on the left side, surface reflectivity is 7% we say. But you are making a lot of constructions. You are making a lot of deforestation. Reflectivity increases. So it could be that 7 can be becoming maybe 7.05. So it is going to change again the energy balance of the Earth atmosphere. This is called climate change. So Trendmatter produced this figure by combining these not just observations alone, not by observations alone, but by combining, assimilating data from various sources, various observations around the globe, and satellites together with models, assimilated data, right? So this is getting refined, and most recent also came. I think 2018 also came. But this figure, it was very attractive to me. So later on, it is becoming a little bit more. Keep on getting involved. I wanted to make this as a very primitive thing. Now I would like to tell you why I am putting this here for bound layer. You look at the pink numbers. I told you that solar radiation, excess radiation at the surface, deficit in the atmosphere. This energy has to be balanced. It means the energy has to be transferred from the surface to the atmosphere. Entirely it takes place through bound layer. So bound layer processes are primarily responsible because convection has to take place. Air has to move, and air movement in the bound layer will be fully controlled by the state of the bound layer. So that 29 that comes in the energy balance entirely comes from the, I will not say coming from the surface, but passing through the bound layer. So bound layer can modulate the numbers. All those numbers can be modulated. And it is the other way also. For example, latent heat flux, sensibility heat flux can modify the bound layer also. So it is not just that bound layer controls them, but the bound layer also can be controlled by them. It's called a feedback process. And once you enter into that domain, it becomes a real challenge because the nonlinear processes which are coming in there are least as understood. There's enormous scope still in that. That's why we always, even now we are trying to find out what is the kind of, latent heat energy that is going under various conditions, at various surface conditions, at various bound layer conditions. So this is one of the active areas of study, even today. I think you also have a system, a ready covariance system. The primary objective is to do that, and it varies with region. I will come to that in a short time. Now, about the Earth, I would like to tell you one more thing. When a parcel goes up, about the atmosphere, when a parcel goes up, suppose, people are often confused with air parcel going up. Where is the parcel of air? Okay. But atmosphere becoming infinity, the air that is here is not going to interact with the air that is 100 kilometers away. So you assume a huge parcel of air, huge chunk of air, not just 1 kilogram. Then, except at the boundaries, it is not going to interact with the environment. If you take 1 meter cube, it is definitely going to interact with the environment in no time. But if I take a 100 meter cube or 1000 meter cube of air, it is not going to interact readily straight away with the outside environment, but rather it is going to go up like that, except in the fringes. In the fringes, there will be exchange which is taking place. We are not considering that area. We are considering that that well within that you have an adiabatic process. That is, you are not giving to the environment. Remember, if this to take place, if you take simply without a boundary, it is not going to take place, because always atmosphere doesn't know that there is no air parcel, no fluid mechanical equation. It behaves by its own way. The second is, there's a time scale involved in all these things. Suppose I take this parcel next year computation, nothing will work. It has to be very quick. Adiabatic process especially has to be very quick, because otherwise, with the time, it is going to interact with the ambience. So you have to consider those. So bound layer processes are quick. For example, when you have a deeper convection coming, convective system is huge, and that fellow take place within hours, maybe within an hour, maybe within a few minutes, as far as convection is concerned. So you can consider the first principle, you can consider it as an adiabatic process. Now I consider an volume of air, which is rising, which is not interacting with the environment. Interacting in the sense, no energy is exchanged between the parcel and the environment. That's all what it is. Environment will keep its own temperature, parcel keeps its own temperature. It is possible. It is really possible. You can see a bubble that is coming out. It preserves its property, but it is not indefinite. Within some time, it will be going out. Under that condition, adiabatic process means heat exchange is equal, dq is equal to 0. Now you have studied in your +2 and all those things. When a parcel is going up, it has to do work against gravity, and also pressure is decreasing. So this is a combined effect. Gravity, doing work against gravity, lower pressure, all these things are combined effect. We have seen adiabatic equation, exponential decrease in pressure. Second is, internal energy of the parcel changes. What is internal energy? Internal energy is nothing but CV dt. That is the energy that it carries because of the temperature of the body. So dq is equal to CV dt plus kdv. This is very well known equation. We don't have to deliberate further. And dq is equal to 0 for an adiabatic process. That means a huge air parcel, if you take inside, this is the weight is up. In that case, pdv is equal to minus CV dt. And simplifying this, and also you are assuming that pv is equal to RT. Then pdv plus vdp is equal to RDT. In which case, for a perfect gas, Cp minus Cv is equal to R. You can modify this equation, and finally you will come to the bottom of the equation. For an atmosphere and hydrostatic balance for an adiabatic process, Cp dt is equal to minus G dz. It comes from very simple thing, VdP. VdP, you are changing dP by the earlier thing. So V rho G dz. This is a simple derivative. This you will get. It is already available here. You will be able to derive in no time. So finally, it happens that Cp dt is equal to minus Gd, minus G dz. G is the acceleration with gravity. D is the displacement, vertical displacement. This is because V is 1 by rho, because we are talking about specific volume. We are not talking about volume 100 meter cube and all. We are talking about specific volume. Under that equation, I am just continuing from the last statement. Cp dt is equal to minus d by dz. Now, what should be dt by dz? dt by dz means the rate at which the parcel as it goes up. What is the rate at which its temperature will decrease or increase? That is dt by dz. It is equal to minus g by Cp. And remember, for a dry air, this is universal. Water vapor should not be there. If an infinitely large air parcel is going up, its temperature is going to decrease at a rate minus G by Cp. G is constant, Cp is constant. G is varying with altitude, but it is within around tropopause and all those things. You can neglect the effect, or even if you don't neglect the effect, it's going to be very minuscule. Okay. So this is called dry adiabatic lapse rate, and if you convert it, you will find that the value is 9.8 Kelvin per kilometer, and sign has to be negative because it is decreasing. So actually, I did not put that negative sign. Sorry, it has to be negative. All right. What is its significance? It has tremendous significance. I will come to that in no time. The second aspect is, what if the atmosphere is moist? Because moist also, it will be going up. It is not exchanging with the environment and all those things. But what happens is, up to some level, it will be cooling at this rate, minus 9.8 Kelvin per kilometer. Then once it starts reaching the dew point, it starts condensing. Once it starts condensing, latent heat will be liberated. Latent heat liberated is now added. Instead of subtracting the energy, now it is added. So it will not be decreasing at minus 9.8 Kelvin per kilometer, but rather at lower value. Typical value can be, say, 3.5 or 4 Kelvin per kilometer. depending on how much is the moisture that is contained. It will vary depending on how much is the moisture that is contained and what altitude it has to have. Both it will be depending. It's not. Whereas gamma D is not like that. Gamma D, that is dry adiabatic lux rate, is not like that. It is constant in the dry atmosphere. If an air parcel is rising up, this is what it is going to happen. This has a critical role in atmospheric stability. I'm linking it with the bound layer before going to the core body. Now we have to define a few terms. These are actually conceptual things, and it is very simple. We know that ideal gas law, PV is equal to RT. You can say PV is equal to nRT. You can form, depending on what is the definition of R. It can be gas constant for unit mass or universal gas constant. Depending on that, your nRT or RT, that will change. Then you will put R star T, whatever. I'm not going into the details, but let me ask you this. I have a parcel with a temperature 300 Kelvin, but its density is 1 kilogram per meter cube, approximately, maybe 1 point. But as I go higher up, density decreases. I still have 300 Kelvin there. This also is 300 Kelvin. That also is 300 Kelvin. Which one will have more energy? If I compress the whole thing. But now I cannot compare this 300 with that 300. The reason being, here that 300 Kelvin is distributed among so much mass, whereas it is among a lighter mass. Suppose I want to compare this, one of the parameters that is required is called the potential temperature. But what does it mean? You compare them in the same platform. So what you do is, you bring that air here at the surface or at a standard pressure level. What is its temperature? That's called potential temperature. Then you can compare all of them together. For example, I have a air parcel sitting at 1000 hectopascal, I have under 250 hectopascal, I have some other hectopascal. All of them put together in a common platform, same 1000 hectopascal. 1000 can be taken as a standard. What is the temperature of the parcel? And the parcel has to be brought adiabatically, means it should not exchange with the environment that it loses its energy. That is called potential temperature. Okay. So then only you can have a comparison of the state of that parcel, thermodynamic state of that parcel with the thermodynamic state of this parcel, especially for heat content. There's one more thing which I would like to bring to your attention. I told you that PV is equal to RT. Now I have two options. R is R by M, R star by M, the gas constant per unit mass. Now you take for the existing mean molecular weight. That mean molecular weight changes with water vapor. Because if today here it may be 30 gram per meter cube, at Saudi Arabia it may be 2 or 5 gram per meter. Now I have the option is which with each altitude, with each location, correct the R. So instead of doing that, you can do another way, a reverse way. Let PV is equal to RT be fixed R, change T. Whatever effect that it has to come in R, instead of going to R, you change in T. That means for PV is equal to R to be RT to be still intact, and with R for a dry air, what should be the temperature? That is called the virtual temperature. So virtual temperature you cannot measure, but virtual temperature is a concept because as the moisture changes, otherwise you have to PV is equal to RT equation, you have to correct for R. And that becomes more involved. Very easy thing is correct for T, and I am coming to that. It is very simple to correct for T.
Can you repeat in virtual temperature?
Virtual temperature, actually PV is equal to RT, it is a gas equation. Yeah, we'll come to virtual temperature first. PV is equal to RT. That is the ideal gas equation. R is gas constant. Gas constant for dry air is what we are taking. But actually, air is not dry, air has moisture. So, as the moisture content changes, value of R will change. Because R is R by M, that is mean molecular weight you have to divide. So, then that becomes complicated. Means every time R is keep on changing. Instead of that, do a reverse way. Keep R the same. That adjustment that is required in R for PV is equal to RT to be still valid, make that change in T and say that the temperature you correct, and that corrected temperature is called virtual temperature. That virtual temperature is, you cannot measure the virtual temperature, your temperature you are measuring is actual temperature. But virtual temperature is for gas law to be applicable with the R value for dry air, what is the temperature that is to be enhanced? Actually, temperature has to be enhanced. How much temperature enhancement is required? That equation, next equation gives you TV is equal to T. TV is virtual temperature is equal to T into 1 plus 0.6332. Okay. This actually 0.633 come from the thermodynamic equations, and then you are you are taking the values for each one of them and then finally putting. I'm not going into those details here. So this, if you keep and simply adjust Q, you don't have to do anything. And you see Q is equal to 0, TV becomes T. And the moment Q is enhancing, that is the specific humidity is enhancing, then you have to correct for T. This is called the virtual temperature. All right. Potential temperature, you have density decrease with height, and it is occurring at a higher height. I want to, because now their density is very low. I want to have a comparison of the energy content of the air, thermal energy content of the air at a upper altitude and at a lower altitude per unit volume. Then I cannot compare them because they are at two different densities. So I have to bring that parcel to a uniform thing. So when I want to compare them, I have to have a uniform standard. Like in colloquial language, they say compare apple with apple, not apple with oranges. Okay. So you have to compare at the same state, means pressure level becomes the same. So now I have parcels at different levels, 1000 hectopascal, 700 hectopascal, all those pressures you have air parcels. What you do is you convert what will be the temperature if that parcel is brought down to the standard level, that is 1000 hectopascal adiabatically. Adiabatically means it doesn't lose its energy. It doesn't gain its energy either. It preserves its energy. Then what is the temperature of that? That is called potential temperature. That is a very important term. It's a very important term, and most of the equations, because potential temperature is something which is conserved. Okay. So we consider potential temperature as the most important term as far as thermodynamics is concerned. And the total energy content of any parcel is Cp theta. You can simply take Cp theta. It will be, and how theta is calculated? There's again a derivation. Actually, you can derive it. When we say it is brought back and all those things, you don't have to bring it back. No experiment required here. Simple thermodynamic equations will convert it. The final conversion is theta is equal to T into Ps. Ps is for standard pressure. Denominator is P, from which it is being brought. P is the pressure at which that parcel was there. So Ps is standard pressure, which we take as 1000 hectopascal, to the power R by Cp. R by Cp remains constant. Now you see, you can easily convert. Just assume P is equal to Ps, 1000 hectopascal, temperature doesn't change. P by Ps, power anything, let it be there, theta becomes. Now assume P is very low and Ps is very high. Ps is standard, P is very low. Ps by P becomes very high. So theta becomes much larger than T. So in most of the conditions, when you have the temperature remaining constant with height, your potential temperature will increase with height. And I will tell you why it is important in the next thing.
Any parcel from 500 hectopascal this reference level, vessel level.
1000.
Okay. So it will be around like
To the power R by
Cp.
Cp. R by Cp is that value point some value. So to that extent.
Temperature will be increased.
Correct. Right. And you should have an equation for, you should have a program for converting these things, because you require these things very often in any thermodynamical analysis. Right. In fact, there is something called a Tephigram, T5 gram. In that, one of the coordinates itself is potential temperature. Because instead of comparing with standard temperature, because density changes, ambience changes.
So with height, potential temperature is increasing.
Potential temperature will increase provided your temperature is remaining constant. Suppose your temperature is increasing anyway, potential temperature also will increase. If your temperature remains constant, then again potential temperature will increase. In fact, even when your temperature is decreasing to an extent, potential temperature will increase. But beyond a certain value of decrease in rate of temperature, that will come to. That is called atmospheric stability. We are coming to that. Now, this is what happens when a moist parcel of air is moving in. Okay, y-axis is the altitude, x-axis temperature. Now the blue line shows what is there. Temperature varies in environment. That is, when you have a radius on day profile, what you have is the blue one. The radius on day measures whatever temperature into the ambient cells. Now you assume you have a huge volume of air that is rising. You just assume yours. It has to decrease its temperature at 9.8 Kelvin per kilometer. So it will keep on decreasing. That is a red line. Okay. This, cursor is not moving. It's okay. So initially temperature decreases at 9.8 Kelvin per kilometer and come to a place. Now you see it has flipped. It has changed. Why? Because at that particular place, it reached a dew point temperature. Means now water vapor in that start condensing. That's called a dew point temperature. And let me tell you, that is the place where clouds start forming. That way it is also called the lifting condensation level. If I lift a parcel of air, all the things which you see in the environment with a stretched membrane cloud, base, top is not stretched membrane, but bottom is stretched membrane. You have that level, that bottom level come from LCL. And it is because of this process that adiabatically parcel was going up. And it reached the lifting condensation level, means now it started condensing. And once it starts condensing, now still the fellow is going up. At 9.8, dry adiabatically it has to decrease. True. But it is also getting heated because the latent heat that is liberated by the water, condensed water. So it will not decrease at 9.8, but it will increase. I mean, net will be around say -4 or -3, whatever. It will still decrease only. It will not increase. It will still decrease only, but it will decrease at a lower rate. It will simply go up till that condensation is over now. Not that all moisture is over. All moisture need not be over. Moisture can still be there, but it cannot condense now. I mean, supersaturation is over. That is the second flip point that you see there at the top. At the top, you have that red line going with a constant slope, and then flip starts. Above that, again 9.8, because there is no other. But there is a beautiful thing which is happening here. You just compare these two. The temperature, the parcel was going, the temperature was decreasing. And the temperature had the parcel had a lower temperature than the environment. There's a problem. Lower temperature means the parcel will be heavier. It cannot go. So it has to be forced to go, otherwise it will not go. Okay, because the temperature is lower than the environmental lapse rate. So the temperature means lapse rate is lower than the environmental lapse rate. So that the parcel, ideally speaking, parcel is cooler than the environment. It will not go. It has to be warmer, then only it will go. So up to that process, somebody has to push it. We'll come to what are the pushing mechanisms. There are pushing mechanisms. So somebody has to push it. So it will go. And it start changing its lapse rate and cross over the environment lapse rate at a particular point. Above that, it is level of free convection. It simply will go. No further pushing is required. But up to the point where these two things are crossing over, pushing is required. Otherwise, that fellow will not go. Okay. So above, once it crosses above, it becomes free convection. It will simply go by its own. Nobody need to push it. And after some time, again, the full moisture, I mean, condensable moisture is condensed. Still moisture will be there, but it will be under saturation. So it will decrease at dry adiabatic lapse rate. And again, it crossed over. Ideally speaking, you will have parcel going up till that particular point. It's the top point where you have again crossing over. Ideally speaking, it will go up to that. So if you push a parcel from the surface, I kept the same axis for both of them. You see, red and blue curve at the bottom are joining together because I'm taking a parcel from the same environment going up. It decreased, but it became cooler. It crossed over at one particular point because of latent heating, and then it is level of free convection. And then again, it started going opposite, level of inhibition. So further, it cannot go up. It cannot go up unless it is forced. If it is forced, it can go. Otherwise, it will not go. This is an ideal condition. Okay, but in principle, I put only LCL there. I did not put the other, cloud top and all those things there. Ideally speaking, cloud top can also be there because cloud has condensed. Condensation has taken place at one place, but cloud can be transported also. So, which is not at the place where it has liberated the latent heat, but the cloud bunch has been transported a little bit more vertically up. It's possible. So we cannot say that no, heat is also dumped there. You have to keep all these things in mind when you are talking about clouds. These are the details. Otherwise, when you start thinking about that, then only it becomes really complex. So this is what is really happening when a parcel of air goes up. Now I told you it has to be pushed, so it has to be triggered. It's called the forced convection. There are multiple ways in which the lifting can take place. One process is you have a mountain, you have an air that is coming in horizontally. It has to go up above the mountain because now there is a forced air blowing and a hard boundary. It has to rise. This is one process, a typical example. Second is the surface get enormously getting heated up due to certain things compared to the surrounding environment. A small region gets heated up, then that becomes warmer. That fellow can go up till it loses its energy. That's called, actually there's a later on method which you are going to apply. I am sure that some of you may be applying it. It's called the parcel method to determine boundary layer height in radius on the problem, not radius on the big problem, the micro radiometer profiler, because its resolution may not be every time adequate for finding small fluctuations in temperature and to find the boundary layer height with accuracy. You follow normally, I'm not talking all cases, parcel method. So parcel method tells you find out what is the potential temperature of the surface air. Find out the altitude at which the same potential temperature, you take a radius on the profile or your MRP profile. Find out the altitude at which the temperature becomes equal to this potential temperature. Up to that, this parcel can go. Above which parcel will not go. We'll come to that point again very soon. Now I am telling you the atmospheric stability, instability we discussed here. As you go level of cloud base, we have seen that is level of what is that cloud level, lifting and sensation level, lifting and sensation. Yeah, sure.
So you showed here weight adiabatic lapse rate is just crossing to the environmental lapse rate.
Correct.
It is always fixed up to that high. You put it at 1 kilometer. It will be vary.
Oh, it will vary. Actually, 1 kilometer is only for understanding that I kept. Like, for example, somebody can ask whether it is 10 kilometer or 20 kilometer. It will substantially vary. Only that total scale sizes I wanted to put in. Not that at 1 kilometer it will be. It will vary depending on how much is your water content. For example, you go to Saudi Arabia. This fellow will not take place at all because it's all dry air. How much is the mass of air? I mean, a temperature it has, it will go up, but it will not cross over. It will simply keep on going. So it cannot reach the tropopause altitude at all unless you have huge energy at the surface. If it is there, then it can go definitely. But usually it doesn't go. That's why all these dust storms, they get generated, lifted up, but it will not go to very high altitude. There is a limit. Whereas CB clouds, cumulonimbus clouds, they reach tropopause or even they cross the tropopause. Volcanoes, volcanically emitted gases. I know that I'm not talking about the rocks. I'm talking about gas emission that is coming. It is not because of latent heating condensation and all those things. It's simply because the initial energy is so high that it can go. So that is, I told you, the trigger. That trigger can be a very warm thing. Volcanic eruption is an example of that. Of course, volcanic eruption we cannot compare with this. The reason being, what is erupted has an entirely different property, density, and all those things compared to this. I'm only telling a corresponding example. Now, what happens if the parcel is going up and then it is not condensing? That is the initial portion which I kept. Okay, and I put one condition. What I did is, you see that x-axis is temperature, y-axis is Z, but instead of the parcel, earlier I considered the parcel at the surface. Now I am not considering parcel at the surface. I am considering the parcel at the point A. Okay, at the point A, which is at an altitude, maybe 1 kilometer, maybe 500 meters, whatever altitude. Now I am pushing this parcel due to certain reason. Okay, the parcel will go up, it will keep on getting cooling. It is no more getting energy to go up. So it will go up to a level where I have pushed it, the energy associated with my pushing. But at every step, it is getting pulled because of the heavier weight of it compared to the environment. So it want to come back. It is like a simple pendulum. Simple pendulum want to come to the minimum point where the potential energy is minimum. Correct? A simple pendulum when you are oscillating, it want to come and stop here. But now you see that parcel, it is, you have kicked it going up, but every time it is feeling resistance because restoring force has to come back. And what happens is it will now start coming back. It will go up to that and then start coming. Up to that point, it will be accelerated because you see it is heavier than the surrounding. It will come back. It wants to stop there. But actually acceleration is maximum at the point A when it is coming down. And it will come down. Now it is getting warmer than the environment. But it is being pushed by, that much energy is still there. It will overshoot that point A. But then onwards, it will get warmer. And then again, it cannot stay there because it wants to go. This fellow will keep on going up and down, up and down, up and down. This is continuously happening in atmosphere. Continuously, anytime. And this is one of the most important parameters in the atmosphere. It's called a Brun-Weisler frequency. It is in a stable atmosphere. Brun-Weisler frequency exists only in a stable atmosphere. It is not existing in an unstable atmosphere. Okay. So the Brun, I will give you the total thing. This is already available here. So this Brun-Weisler frequency, it will actually start oscillating back and forth, back and forth, back and forth. It has a lot of implications. First thing is, that is the highest frequency oscillation that atmosphere can stand. There cannot be any other oscillation which has higher frequency than this, which atmosphere will be able to stand. Mechanical oscillations. Like for example, gravity rules. We say gravity 10-minute periodicity, 100-minute periodicity, it can have. But minimum thing will be Brun-Weisler frequency. Below that, if anything is there, atmosphere will not be able to support and it becomes turbulence. So turbulence scale start from lower down. After that, it is in principle able to oscillate. And this is what I already told you, so I will not go further deeper. And Brun-Weisler frequency you can calculate. You simply take d theta by dz, g by theta. You will get Brun-Weisler frequency. And I would like to bring to your attention one thing. Why so much Brun-Weisler frequency? Just assume, you know NAR, National Atmospheric Research Laboratory. Yes. There's an MST radar there. Yes. What MST radar detects? It will be detecting an echo that is coming, and it will be able to measure Doppler. Doppler will be associated with wind. It can also be associated with the vertical oscillation if Brun-Weisler frequency exists there. So it can detect the Brun-Weisler frequency at any altitude. It is actually giving continuous profile. So it can detect Brun-Weisler frequency at any altitude. Now I know d theta by dz, n square is related. I can invert back what is theta. And if I know what is theta, I can invert back what is the temperature. Actually, can you imagine a radio radar can derive temperature from that through this simple concepts. And this paper was published by Revati Madam, BVK. You know BVK? Dr. B.V. Krishnamurthy? The doyen in the atmospheric space science. One of the greatest scientists India has produced in this. And this was his idea, and Revati Madam is their group. And that is the importance. So there are various other applications. So I'm not coming to all those things because our main topic is not that. This I'm coming because of the importance of stability in the boundary. Now you just take virtual potential temperature. Instead of potential temperature, you take virtual potential temperature because if moisture is there. So equation is the same, except that instead of T, you put TV. If potential temperature is increasing with height, atmosphere is stable. The air cannot go up. The air from here cannot go up if potential temperature increases. You can derive potential temperature profile. You have a radius on the temperature profile is there. You can derive what is potential temperature. So if virtual potential temperature is increasing with height, atmosphere is stable. No weather will take place. Weather in the sense no clouds, no convection will take place. I will not say no clouds will take place. Clouds will still take place. That I'll come to. But no convection will take place. If it is d theta by dz is less than 0, you close your eyes and say it is unstable. The air parcel will continuously go. Okay, so it will be convective. And if d theta by dz is equal to 0, it's called a neutral. Means I take a parcel, I place it, it will go up to the place where I placed it. It cannot neither go up or come down. It will go up to a place where I have placed it. That is neutral. So stable, unstable, and neutral. And this is most pivotal for boundary layer research. You know atmospheric layers and all those things, and bound layer is the bottommost layer in the troposphere. Okay. So,
physical significance of this one, d theta by dz, if greater than 0 means it's more stable. And
if d theta by dz is greater than 0,
stable.
then it is stable. Means a parcel of air, you have air here. This air cannot go up. If theta is increasing with height, means d theta by dz is greater than 0. It can go up only if d theta by dz is less than 0. In boundary layer, all these three take place. We will come to that. There will be more practical example. And I'm not going to deliberate on atmospheric layers and all those things, but I want to just tell that the bound layer is the lowermost part where the temperature rapidly decreases, but it is not that always temperature will decrease. Temperature can even enhance. That is why we say inversion layer. We'll come to those. Now we are actually starting. We have given an introduction that is a prerequisite for the other things, but it will be also helpful in our cloud lectures. So the bound layer. Bound layer actually is not just for the Earth alone, Earth surface alone. Bound layer, various bound layers exist. You have a magnetosphere, you know that? Solar wind comes and interact with the Earth atmosphere. There's a bound layer there. There's a shock region. All those kind of things are taking place there also. So magnetospheric bound layer. You have an aircraft that is going. It has a bound layer. This bound layer is very close to the body. Very close to the body, unlike 1 kilometer for us. And in fact, the bound layer dynamics of the aircraft is so critical, hypercritical, that you have to have very minuscule details about the turbulence and things like that, which is taking place. I'm not going into the details. I'm only giving you another dimension. Actually, what is shown here, the shuttle, the temperature at various places is what is shown. All what it does is it travels through the atmosphere. So the friction that it faces, that comes from the boundary layer of the vehicle. I'm not saying atmospheric boundary layer, it's boundary layer of the vehicle. This happens for aircraft also. One thing which happened to me, which occurred to me, I thought I should bring to your attention. We will not deliberate further on this. Neither I am an expert in these things, but it is a very interesting thing. You see the aerofoil on the left side. That is actually the wing of the aircraft. Correct. At the front point, you have a stagnation point. Then you have the curvature, and the flow is very fast there. It will be very speedy. Correct. That's called a turbulent bound layer. And there's a transition between stagnation point, laminar bound layer, and the turbulent bound layer there. And that is decided by the wind speed and the shape of the airfoil. Okay. And if you take the wind, that is the right graph, you have the solid line, that is the body of the aerofoil. Now, at one side, with the distance from this, you can take it as altitude from the body of the foil, how wind speed is changing. Wind speed changes, right at the surface, wind speed will be, the molecule will be traveling along with the vehicle. So you consider it as 0. Of course, it will not be right at the surface, there will be small displacement there that we will come to. And then it logarithmically increases its velocity. See, it is logarithmically increasing. Remember this term, logarithmically increasing, not exponentially increasing, logarithmically increasing. Okay. Beyond that, you see, this is the scale is logarithmic. You see on the right, and this time it is not able to generate turbulence at that particular place. Or the turbulence, I will not say it is not able to produce turbulence, but turbulence is minimum. Whereas on the other side of the aerofoil, you have sharper gradient in wind, which is happening, which generates turbulence here. And this happens for the total aerofoil situation. Now you see the pressure, how does it vary? Static pressure, that is the bottom. The scale, actually the left figure is fully for that vertical line you see, its corresponding points are marked. Okay. At the beginning, the pressure is something like ambient pressure. At the end, the pressure is slightly, that is at the tail end, the pressure is lower. The red curve, the pressure is lower than the ambient. But you see, there is a dipping point that is coming at the bottommost. That is at the place where you have the, and you see that there is a point of airflow separation. You see that top graph, the middle Y graph. There's a flip point. There is a point that the flow is fully separated from the spacecraft, and you can notice this. Next time when you travel in an aircraft, you sit near the wing and look at that from the side window. Certain times, especially it happens when you have the high wind speed is that is headwind or tailwind during the landing and takeoff time. And at that time they will also tilt the aerofoil for getting that. It is not just the speed road, but aerofoil, direction also matters. You will find that there's something like a smoke that goes over that. Underneath it is clear. Above that it is clear. And it is something like a smoke that is going. It is not smoke. There's nothing smoke there. It's actually the flow separation taking place there and the kind of turbulence. So you can see these things visually yourself. So this is a bound layer and very similar bound layer is there for the Earth. And the best bound layer physicist in the Earth that I have come across is Pierre-Dox. Pierre-Dox knew that above the bound layer, you have the logarithmic variation in wind. And they are digging their thing inside. And no air circulation will take place if I dig a hole and connect to them. Because there has to be an entrance and exit, because that is their safety. So no air circulation will take place if I'm keeping it in the same plane. Okay. So what they do is, they take one at a slightly hilly. It will not be a mountain and all those things, local hilly thing. And then slightly lower one entrance at the base of it. What is happening is air velocity is, we told that it increases rapidly with height. Very clear, close to surface, it will be very minimal. But you see, this surface is undulating. It is that ideally speaking, every air velocity has to be exactly zero right at the surface, but then surface is undulating. So if you have a small height that that is taking place there will be higher wind speed. At the other place, there will be lower wind speed. Now you see Bernoulli's principle. Air will naturally circulate through. So the fellow is safe. Air will naturally circulate through. And all the bound layer that we are talking about, the Pierre-Dox, and it is designed in the Pierre-Dox world. There are several examples like this in nature, where they make, I don't know who taught them all these kind of things, but they neither know Bernoulli's principle nor bound layer physics, but their houses are made like this. You can see actually in National Geographic and all, they go in. It is all their safety. And in fact, in more detail when you go, you will also get where do they sleep. All those things are also constructed in such a way that the circulation comes and then get out. And they have traps, like somebody cannot simply go in and then attack them inside them. Their design is like that. This is a very simplistic thing. Now, what is bound layer? We'll talk about atmospheric bound layer. Atmospheric bound layer is actually the lowermost part of the. It is very close to the surface. And what is most important, fundamental definition is, it responds to surface forcing. What is surface forcing? Surface get heated up. That can be a forcing. Immediately it responds. And the total response time, even the response means response will not be right at the surface alone. It has to be transferred to the atmosphere. It cannot go up to 100 kilometer, 10 kilometer, 5 kilometer. No. Within an hour sort of, up to where it will be able to respond. That is called bound layer. There is one more thing, that the air parcel, if it is freely lifted, up to where it will be able to go. That's why I told the parcel method. Parcel method is, what is the particular temperature here? It will be able to go to the atmosphere up to that particular temperature. Ideally speaking, the classical definition of this, that is what I have written here. It is directly influenced by the Earth and responds to the surface forcing. Surface forcing can be warming or cooling, both can be. For example, if an eclipse occurs, or a cloud, by eclipse, cloud pass through, immediately surface will cool. You can, you have the ground observatories with you. There are soil temperatures with you. You have solar radiation with you. See, immediately the moment you have a cloud coming, surface will start cooling, because surface specific heat is very low. Immediately it will start cooling. Water is not like that. Water specific heat is higher. That's why you have sea breeze, land breeze. Now, up to where this fellow can go, ideally speaking, it will be going up to 100 meter or maybe 3 kilometers. This is the maximum. There is no upper boundary, hard upper boundary. Depending on what is the parcel's energy that it has, it will go up to that. But, and one more thing, the moment clouds start forming, you will not say that cloud is in that boundary. Actually, bound layer is in the base of the cloud. For example, a convective cloud, especially convective cloud. When you are having, most of the clouds which you see are not convective cloud, but rather accumuli, that white puffy cloud, they are formed at the top of the boundary layer. Okay. So this is what the bound layer. But then it is not that a single layer of bound layer exists. Actually, boundary layer is again divided. This equation I will, maybe most of you may be already knowing, this is actually the fluid mechanical equation, Navier-Stokes equation in vector form. It contains the acceleration term, total acceleration come from the local acceleration and advection, which is actually gravitational acceleration, pressure gradient acceleration, Coriolis force, and the last term, frictional acceleration. The frictional term is there only for the boundary layer. If you cross the boundary layer, you can neglect that friction. I'm talking ideally first order. Friction is always there in the atmosphere. Some amount of friction will always exist. But it is negligible compared to the other. But boundary layer, you cannot neglect. So that is the modification of this. Now this equation has a problem. Equation has a problem in sense. Ideally speaking, you know isobaric flows. I mean, you know, what is that? This is geostrophy approximation and things like that. Flow is parallel to the isobaric. But you have another term that is sitting there. It will not allow the Coriolis force to be balanced by geostrophy. Correct? I mean, Coriolis force to be balanced by pressure gradient force. That's it is called a geostrophy. There's a friction term. So result is, it will actually drive the air parcel into the low pressure. If you have a low pressure, instead of air circling the low pressure at the surface, it will have a cross isobaric flow. It will come inside and kill the low. And that is one of the impact of boundary layer. Because boundary layer, suppose it was absolutely frictionless thing. When a cyclone enters, it would still move farther. But cyclones will be immediately killed if roughness is very high. Because the cross isobaric flow becomes very high. Friction becomes very high. Okay. But of course, cyclone will still die because cyclone is not having energy now. Because in the ocean, it has sufficient water vapor that is going up and condensation takes place and it has energy. But what I'm telling is, ideally speaking, if this fellow is entering and a very low, very less rough surface versus a high rough surface, the system will be killed immediately if surface is very rough, especially, for example, through forests and things like that. We will not dwell into that. But that frictional term becomes very important, the boundary layer, in the dynamical Navier-Stokes equations. So that is the importance. Now, the importance of the boundary layer is it will transfer, I told you, surface, water vapor get evaporated and goes to the free troposphere through the boundary layer. So boundary layer regulates what fraction should go to the free troposphere. If it is very stable, nothing will go. For example, you have fog that is getting formed in Delhi and North Indian belt full, winter time. What is happening? You have potential temperature increasing with the night. So this parcel of air will not be able to go. Now, whatever moisture it is getting condensed, it will be getting accumulated there. It can be condensed because the temperature keep on decreasing. It's called radiative cooling. So temperature is keep on getting decreased. So whatever moisture in the atmosphere start condensing, but it cannot go lift up. So that's why it is called fog. So you see, fog means it is not allowing anything to cross over. There's a problem. Fog is okay. Fog is only an aircraft problem, but it will also not allow aerosols to get transported. Then that is a problem, because you see, for example, a typical example is the Bhopal gas tragedy. It occurred in the night. Boundary layer height is very low in the night. So the whole thing get trapped. After superposed on that, it was going in a cone. So it spread along that cone of wind. Other part of the city was not affected, but this part of the city where the air was going, if it was going up, it would have been diluted. I'm not telling there will not be any effect. It will still be, there will be an effect, but it would have been diluted. So that is the importance of boundary layer height. Boundary layer height decides the ventilation. Actually, it's called the ventilation coefficient. Boundary layer height multiplied by the mean wind speed is called a ventilation coefficient. That is an index in the pollution research. So I told you about the exchange of moisture is one factor. Greenhouse gases is another. Aerosols is another. Then overall, we are considering latent heat of evaporation, latent heat of condensation. So latent heat flux and sensible heat flux, energy exchange. There's one more term, momentum flux. You know that Earth is getting retarded or accelerated depending on the wind, tidal effects. It can have a minuscule change, millisecond change or microsecond change in rotation speed of Earth. Today's rotation speed of Earth may be one microsecond than yesterday's. Can be, depending on the wind speed. Because the momentum is transferred through the surface. You see that wind can retard it. So, but then all those things are decided by the wind system that is prevailing in the boundary layer. Atmospheric residence time of aerosols. For example, boundary layer, you have a heavy particle that is cold. It will be flowing, falling back immediately. But if there is high wind, it can be still transported farther. So residence time will be again decided by the boundary layer. And of course, that obviously means that dispersal also. Development of clouds, convection, precipitation is first thing start with the boundary layer, because top of the boundary layer is a place where clouds start developing. Long range transport pollution, boundary layer doesn't directly affect, but boundary layer decides how much is the thing which is exchanged to the free troposphere, where it goes for long range transport. So boundary layer is one of the most important factors to study there. And boundary layer is not a single layer. There are three layers. One is a viscous sublayer, which is very minuscule, within a few millimeters, where we told, there is no wind, you cannot have a huge wind system there. Because right on the surface wind has to be negligible or close to zero, or equal to zero. At that place, the exchange takes place through diffusion. Still exchange takes place there, but that takes place through molecular diffusion. This is one of the least studied thing as far as the Earth's surface is concerned. And because it is highly varying from one point to the next. And in a large scale dynamics, its effect in the model and all those systems very low. And it extends only a few millimeters. But then it is very interesting things to study about. The next level is the surface layer. So boundary layer, ideally speaking, most of our practical applications, we have to separate into two. The surface layer and the boundary layer. Because surface layer, you see the wind speed was rapidly increasing. Above that, that's why we say logarithmic. It just went like this and it was running steady. So the place where you have the largest shear, that is the boundary, surface layer. There, what are the processes taking place? All the energy, all those kind of things come there. What is most important is the vertical momentum transfer of eddy, turbulent eddies take place through the surface layer. It extends from almost 10% of the, up to around 10% of the boundary layer. It's not a hard and fast thing. It's a thumb rule. Like for example, if 1 kilometer boundary layer, you can consider 100 as there, but it doesn't mean that 100.00 is stop. It can be, you can take it as slightly below or slightly above. Okay. And the Ekman layer, Ekman layer. I think once we go into those deeper, we may take much longer time. The time that he allotted to me was 12:30. It is getting now. I may extend slightly further because we started a little bit late. The wind, ideally speaking, right to the surface wind has to be zero. Now you have a pressure gradient. So for that pressure gradient in the free troposphere, there has to be, geostrophic wind, but it will never reach a geostrophic wind. Ideally, in the boundary layer, what will happen is, it will increase. It will actually go higher, and then there's a spiral kind of thing that will happen. This is called Ekman spiral. The same thing happens for ocean also. Right at the surface of the ocean, now you have a flow, but interior, the direction changes, then it forms a spiral, and that is very important for oceanography, especially coastal upwelling and things like that. It's a very, very important thing. We'll not dwell much into that. Maybe we can have a discussion if you want later. And this is a schematic of that. You have the interfacial layer, which is within the first few millimeters. Then you have up to around 100 meters if the boundary layer height is close to 1 kilometer. Around the turbulent transport becomes very important. Turbulent eddy formation and the transport becomes very important. That's called surface layer. And above the surface layer, where you still have the convection going up and then significant convection going up and the boundary layer. So this we already told, and the common variables that we use to define them is temperature, partial temperature, partial temperature I missed it here, and partial temperature also. Mixing ratio, it becomes very important. Water vapor mixing ratio, and wind system. And remember that Q and theta are conserved for diadiabatic process. Diadiabatic means Q is not changing, mixing ratio is not changing because it is not getting removed, it is not getting added. Same is the case with potential temperature. That's why we use potential temperature. It is conserved. If I take a parcel, it will carry that energy with that. That means potential temperature will be the same. That's why I told the parcel method. It will go up to the place where the parcel's theta becomes equal to the environment. So this is a last statement is a heavily loaded statement. Q is very obvious, but theta is conserved. Ideally speaking, theta b. Boundary layer varies with the geographical conditions. Over the ocean, over the land. Land means it can be mountain, it can be, vegetation type can be different. So depends on the geographical features, oceans, continents, coastal regions, or mountains. There can be also differential heating developed. For example, you have a lake which is a huge water body, and you have both are continents only. and you have the land. Land get heated up very fast, lake get heated up very slow. That's a differential heating. There can be one small circulation that happens within the large scale boundary layer. That's called internal boundary layer. There can be internal boundary layers. Classical example of internal boundary layer is you have sea breeze. You see, over the coast, when you go into the continent, you have a continental boundary layer. Maybe at Tumba, when you consider, around 40 kilometers away, there is no more coastal boundary layer. There is no more internal boundary layer. It is actually convective boundary layer. But the convective boundary layer air must come and then refills. It will come back. Internally, what happens? Now you have a front, sea breeze front that is moving, which has contrasting air mass. That has a distinct change in temperature across that, stability across that. That makes an internal boundary layer. So it's called a thermal internal boundary layer because this air mass carries distinctly different thermodynamic properties. Its humidity may be different, its temperature may be different. So that is called internal boundary layers. And then the most important thing is over the land and coastal region, there is substantial diurnal variation. Over the ocean, diurnal evolution is very, you can neglect. It's not that you can completely neglect anything. There are variabilities, but that variabilities can be. But then there, what is more important is on larger periods, like for example, when a wave is coming, boundary layer can be very shallow, boundary layer can be very high. That happens over the continent also. But diurnal variation is very low because specific heat of the ocean is very high. And there is a larger depth over the ocean where the temperature is not varying drastically, thermocline. So heat content doesn't change drastically. Whereas over the land, you have only the surface that is getting heated. You go a few centimeters deeper, maybe 10, 20 centimeters deeper, temperature change is not as much as the surface temperature. So surface will get immediately heated or cooled. That is why you have huge diurnal variation in boundary layer. Means when you are studying boundary layer, when you are measuring boundary layer, surface becomes very important. Soil temperature, soil moisture becomes very important. Even their profile becomes very important. The second thing is, over the land, you have so much of heterogeneity. This I took as an example, the NDVA, that is an index of vegetation over India. If I zoom in, you will find that from pixel to pixel, there is huge variance.
Yeah. This diurnal variation we will look for daytime only because it will be stable in night time.
No, it will be there for the daytime and it will be for the night time. But you are, ideally speaking, you are correct. During the daytime, you are full heating and even it settled. But not that immediately it will be settling. There will be still diurnal nighttime also. There will be a boundary layer that can be developed because of wind. You know, there is a thing called the solitary wells. There are solitary wells which get generated, which can transfer at one end of the Australia to the other end. It can travel. This is what it is told. It will be, that front end will be actually a roll cloud will get formed and then simply, going to that extent. So nighttime also you can have, especially through solitary wells. There's one more. Nighttime, suppose there is a wind shear. Wind shear can generate turbulence. Turbulence can cause mixing. Boundary layer can be still there. So absolutely calm condition, what you told is absolutely right. Nighttime almost same, constant. Nighttime, it will be start increasing. Your point is right, but I told this as a practical thing, it is not. Nighttime, nocturnal boundary layer becomes very important. Actually, we have studies on that. Especially sea breeze, land breeze, or coastal region. Land breeze becomes very important, and there are solitary wells that were detected, even at Tumba. Okay. So, what I'm telling is the pixel to pixel variability becomes very high, that in a modeling effort and all those things. But at the same time, you cannot have network observatories kept at every pixel. No. So, what we do is we study different geographical conditions, different climate conditions, and try to parameterize them into the model. You cannot have every measurement over every nook and corner to do this. Okay. You just look at Trivandrum. Just look at Trivandrum district, what is shown here. I took it from Google. You can use it. Actually, people use it even in their model. Straight away, they ingest it. It's land use, land cover change. Airport area and where we are sitting, that red area means it is actually built up area. Rural or urban built up area. And then green is actually the vegetated area, agricultural land and things like that. You see, but my point is over very small scales. Whole Trivandrum is embedded here. So within a few meters, maybe 100 meters or maybe within a few kilometers, I can still further zoom in. I zoomed in, but I did not put that. You can even see buildings, a few buildings and then vacant land and then you will have a lake. So there is huge inhomogeneity to huge variability in the surface roughness. So all what we talk about is when you make a measurement, depending on the place your sensor is kept, your roughness length will be different because it sees a volume which is different from, if I keep at 4 meter, the volume that you see, it's called the seeable area, is different from 30 meter. Ideally speaking, we usually follow something like maybe within 30 meter, we make the measurement and then do the calculations. And above all, now today, one of the most important topic is the urbanization, and it completely changes your roughness. And what is more is, I'll come to that in another moment. You have a huge boundary layer that is getting developed in the boundary layer, I mean, in the urban area itself, an internal boundary layer, even in the night, which you are talking. We'll come to that. So crucial factors to consolidate which affect the boundary layer development is topography and roughness. Roughness means whether it is trees, whether it is plain, or whether it is buildings. It is not correct directly coming as roughness. The building height doesn't come as roughness. Roughness is another parameter. It's only an index. Okay, you cannot consider the building height as the roughness parameter. Roughness parameter may be of the order of a few centimeters, or maybe of that order, maybe maximum meter. Surface type, whether it is vegetation, whether it is soil type. For example, even desert varies. Desert or a clay soil will behave differently. Soil moisture becomes very important because you give solar heating, soil temperature will not enhance if soil moisture is very high. And soil moisture adds another thing, get evaporated and latent heat of evaporation goes up. Soil temperature doesn't increase much once soil moisture is high, then sensible heat flux becomes lower. You see how much it can change the boundary layer. And water bodies. Spatial contrast in surface features, which I told you, the boundary layer, the internal boundary layer, lake versus this. And I have seen one paper where you have a forest, you have the other land, that creates an internal boundary. A forest and your urban area, urban means built up area, that itself generates an internal boundary. Okay, so boundary dynamics is very varying in spatial and temporal scale. And large scale circulation also can affect. For example, you have the monsoon coming. For the same conditions that prevail here, you have a background wind that is entirely different. Boundary development will be different because it depends also on the background wind system. And the solar influx. When I say solar influx, you may think that solar influx is the same every time. Solar influx varies substantially with respect to clouds. Influx, I put influx at the surface. At the surface. So influx at the surface will be significantly varying if cloud is there or not. Aerosol is there. This is the aerosol impact on boundary layer, and boundary layer in turn will impact the aerosol. So there are distinctive features over the ocean continents. We have to study all these things separately. Coastal regions, mountain terrains. Highly complex over the mountain. You have some places in the mountain, you will find that there is foggy kind of thing that is lying there. Like you can see in an undulating mountain, one place there will be huge foggy thing, other place peak it will be very clean. See how much it varies in over a meter or a tens of meters, boundary layer varies. That's what it means. But actually, you cannot consider that as a simple boundary layer. But then,
sir, I'm from Uttar Pradesh.
Yeah.
Sometimes I see in 100 meter, just there is a too much fog.
Correct.
Even after 100 meter,
it's very clear. It's very clear. Actually, it is because of the surface changes, surface energetic changes, and associated change in boundary layer, surface layer. It will not take place in the afternoon. It will take place in the morning. Because morning, it responds to, we are told, it responds directly to the surface beneath. So, someplace it may be buildings or something like that, higher traffic can be there, open area can be different. And let me tell you one more thing, I did not put it here. There's something called the Ramdas layer. It is an Indian who discovered it. It's from Indian Institute of Science, Bangalore. There's a layer during, in agriculture fields, flat agriculture fields. There's a layer where the temperature minimum doesn't come to the surface. It is slightly elevated, a few meters, maybe a meter, maybe 550 centimeter. He measured it and we found that it is slightly elevated. And there's an entirely different theory, Rodham Narasimha and people like that worked on that. Okay. So these kind of things happen over flat terrains, agriculture kind of thing, soil. There are so many factors that come in. Actually, it is because the energy exchanges that took place, that is taking place. It's already modern. So these kind of phenomena can take place. When you are going through these, we are from northeast, northern land. When we were traveling in the northeast, when we basin, it was so beautiful that at one place in the evening, because now cooling starts, there's a foggy layer that is just around a meter above you. We know that clean. Just to lift it up 1 meter above, and it is not just a small distance. We are traveling by car from Tezpur, I think, Dabbalgarh to Tezpur. A long distance we were able to see this. See how complex is the boundary layer. The challenges here in the boundary layer is, first thing is very short spatial scale and time scale, temporal scale. That becomes the problem. Non-uniform surface features like ridges, water bodies, vegetation type can affect it. And at the end of the day, we call it as a sub-grid scale process in the model. Because in the model, if you want to do it analytically or numerically, directly, so that pixel to pixel, you like a pressure gradient, you cannot do it because within the pixel itself, it varies. So you have sub-grid scale processes. There are some, for example, a large AD simulation and things like that can directly feed the surface features if it is available. But most of your models doesn't have that. For example, 3 km resolution of the RF. You cannot do this. And second aspect, there is a much more different aspect. Bound layer height is varying, develop very rapidly. 8 o'clock, it may be 7 o'clock, it may be very shallow, maybe 100 meters. By around 11 o'clock, it will reach 1.5 kilometers. Maximum will come from around 8:39 to around 10. Drastic variation. After that, it will still increase, but from 1 kilometer to 1.1 kilometer, 1.2 kilometer. Something like maybe in the afternoon, maybe, or the continental region, it may reach a little bit higher. But it will not be more than a few hundred, maybe 200 meter, maybe there. Most of the development take place in the morning with it. If I have a radius on day profile, you will never capture the diagonal evolution of bound layer because bound layer, ideally speaking, practically, it's not that you cannot do. Practically speaking, 2 radius on days will be separated by almost an hour or 1 hour because you have one receiver. But if you have multiple receivers, you can still do that. But still, your intervals will be finite. For that, the best thing is you have either radar, LiDAR, or your MRP. MRP is an ideal tool for studying the rapid bound layer. I will come to that. Then bound layer turbulence is not characterized, not comprehensively characterized mathematically. It is very, very difficult. Urbanization becomes much more complicated now because surface roughness change, albedo change, IR heat trapping changes. So it develops its own bound layer. Most difficult thing is the feedback effects. For example, bound layer clouds are formed by bound layer processes. But once the cloud is formed, it starts regulating the surface energy reaching. It will feed back negatively. It will cool the surface. It will cool this thing which it has been generated. So this is feedback. It is very complicated. Especially bound layer clouds, effect of that, and aerosols, atmospheric radiative heating due to water vapor. There's an interesting study which we have found. One of my students, I think it is yet to be reported, but it is there in his thesis, That is the radiative impact of the water vapor. Now, water vapor enhancing how does the heating rate changes and how does it trigger the bound layer turbulence in the base? And most complex factors among the numerical models. That is one of the least unknown factors. There are in the models, a few things are creating more problem. One is bound layer. Second is convection. Especially cloud, cumulus convection. The cloud parameterization, bound layer parameterization, these are among the most difficult part in clouds. You can have a comparison. So people make a comparison between what is observed and what is derived from the model. Most of the time, I'm not telling entirely different, but there is significant differences between these. This I already told you, and my point only is that out of that 100 unit of solar radiation, in terms of energy now you take, out of 100 unit of solar radiation, 29 factor is controlled by bound layer, modulated, and that controls, bound layer processes control the exchange between the surface and the bound layer. So you need to have eddy covariance systems and things like that for measuring how much is the sensible part, how much is the latent heating part, and how much is the flux of energy that is going. Okay. At the surface, this is a single one-dimensional equation, surface energy budget. Surface energy budget is what? I have solar radiation coming in, I have solar radiation reflected. I have longer wave radiation coming in, longer radiation emitted. These are the radiative part. Next part is how much is the latent heat that is going in, mechanical. How much is the sensible heat flux that is going in. It will never match. There will be a misbalance that comes. That is called the GS. That energy is stored in the soil. So that much energy will go inside. And in the night, you're told, the night time, will it be steady? No, because night, the soil conducts to the surface, so it will leave a minuscule energy. You can the way to look at it is you find out how much is the diurnal variation of temperature at surface and interior. You will still have a diurnal variation even at 10 centimeter. Okay, means the heat is getting lost in the night, right? So the GS is the heat flux that is stored. You have to have all parameters measured. For that, radiation, you have radiation sensors. You have solar radiation pyrheliometers and piezometers. Your soil probes, for putting in the soil temperature and the storage, ground storage. And for H and E, that is actually sensible heat flux and latent heat flux, you should have faster response sensors because it has to measure turbulence. This whole thing is transferred through turbulence. So you have to measure turbulence, sonic anemometer, and you have to have water vapor or carbon dioxide. Carbon dioxide is not part of the energy, water vapor is part of energy. So this is called a decovariance system. There's another way to do that is you keep sensors at multiple layers, like in a tower, then you can still have an approximation between the layers and you can do. But ideal would be a decovariance system that is kept. That is the best tool for studying the later half. And radiation sensors are very common. But one thing, let me tell you, for practical things, you have to calibrate all these things very frequently. Not that you keep it there and then leave it once and for all, because all the changes that is taking place will be observed in part of the square. I mean, changes in climate change and things. So you have to have a system which is calibrated within that, right? If you do all these things again, ideally speaking, it has to budget. And no textbook will tell you that it will not budget. But let me tell you, it will not budget. It will not budget because budget means balance, sorry. Because of two reasons. One, sea breeze come in, air get advected. Cold air get advected. Heat get advected horizontally. So where is the term here? Advection of heat is not a term here. Radiation came, energy went up. There's no advection term that has come here. For example, if you have a sea breeze coming in, your energy balance equation which you have here, the term will have an excess or deficit of say up to 30 or 40 watt per meter square. That much is the heat that is advected if it is from hot body or cold body, depending on that. The second, measurement uncertainties. So measurement uncertainties, if you have biases, then again it will not be balanced. And let me tell you the heat that we all talk about the sea breeze coming in, sea breeze cooling, sea breeze temperature. How many of us can actually measure how much is the advected heat? Actually, people make these kind of measurements. Okay. So it's a very challenging, it's very interesting. Further studies on sea breeze and these things. And now comes why we should do with the bound layer and with the aerosols, with the climate change. You see, clouds will affect the radiation. Longer radiation coming in, shorter radiation coming in will be affected by clouds. Aerosol also will do the same thing. Aerosol will absorb it, aerosol will scatter it. So your radiative terms will be getting affected. Effectively changing the bound layer energetics, bound layer dynamics, bound layer evolution. So aerosols, clouds, bound layer and precipitation, they should be combined as a single entity rather than treating bound layer as an isolation. Okay. At the same time, bound layer as a fluid mechanical problem can be isolated separately. But when we study, otherwise you have to combine them. There's an interesting thing here. This shows the diurnal variation of temperature we observed it. And the black line is the diurnal variation of temperature. And you told that nighttime, same. Now you see, nighttime temperature is keep on decreasing. And temperature will decrease till sun has raised. Actually, minimum temperature comes after sunrise, not before sunrise. Ideally speaking, in an one-dimensional atmosphere. I repeat. Temperature, surface temperature becomes coldest after sunrise, not before sunrise. Now you see sun is heating, but notwithstanding that, surface get cooled. Why? Because you are emitting, sigma T power 4 is emitted. Solar radiation has started coming in, but it is still lower than sigma T power 4 that you have emitted. Net sigma T power 4, because there is a longer radiation that is coming. So longer radiation, what is lost if it is still larger than solar radiation, that is happening in the low solar elevation, like for example, 637. Temperature, minimum temperature will come up. And then once solar radiation starts enhancing, surface will start heating. So that's why the temperature is increasing. And the inverse relation between them have two effects. One is RH is inversely proportional to temperature. So that may come. But you see there are kinks which are completely different from what you see in the temperature. They are associated with the advection of air mass. For example, sea breeze, humidity. Distinct change in humidity will occur. And the classic papers on how a sea breeze front is advecting and then how it is. Actually, we can talk maybe for hours on those data. It's an amazing work. And this is what you are asking about, how diurnal evolution of bound layer take place. You see here. During the daytime, that is the later part, you see sunrise in the second half, you can see that. And then convective of bound layer is getting developed. Alright? So it is very rapid. You see the later half of this, the green portion. You have the convective bound layer getting developed. But that development is very rapid. And then it will continue. That is the left part. Till the sunset, and you can see the sunset. But before the sunset itself, outlets start collapsing because emitted radiation becomes more than the solar radiation. So after around 5 o'clock or so, maybe typically 4 o'clock or 5 o'clock, even the surface layers start building up. Typically 5 o'clock and later. Surface inversion start building up. That is the black portion. That's called the surface, the nocturnal boundary layer. But that temperature change will affect primarily a region up to maybe around 400 meters or 300 meters. Above that, there will not be huge change in temperature. That's called the residual layer. Residual layer means daytime there was a convective boundary layer. Whatever left there is left, but then nothing new comes. The surface becomes stable. That portion is still left. That's why it is called the residual layer. So aerosols in the residual layer can be still there, residing there, and it happens. Okay, I'll tell you there's a process that's called fumigation. People were observing aerosols, and Subba also, Dr. Parmesan, Dr. Shmuki, they were keep on making measurements. They found that there's a peak in emission. Emission means, aerosol concentration, abundance, come by around 8 o'clock. Initially, people thought that this is actually because, people start going to office. No, it's because the residual layer now comes, you see the other side, the green portion and the residual layer comes and meet at one place. At that time, there is turbulence. The turbulence brings the aerosols from the residual layer. The turbulence has a finite size, it brings back to the surface and then goes up. So, the yesterday's residual layer, whatever thing it was left there, of course, it is not that it is not affected. We are talking about a large scale system now, which is getting transported into the surface because how convective boundary layer is developed? Through eddies. Eddies means they go up and then come back. While coming back, now it has penetrated. The moment it has penetrated the earlier days residual layer, that fellow will come to the surface. It will start a momentary enhancement. It will last only for half an hour. Then it will go. Then it will be further, the aerosol concentration will come down because you have now, getting more ventilated. What I'm telling is, you see the minuscule micro boundary layer features, how does it affect the things here and your interpretation? Unless you have an idea, they had an idea about boundary layer dynamics. That's why they could say that it is actually a fumigation effect. Otherwise, you will interpret it as an anthropogenic activity. Correct? And one figure which I kept underneath is actually, you can see that bottom portion. That's an image over Delhi. You can see the nighttime foggy thing. Now you ask the nighttime whether it is steady. You see, nighttime stable layer is increasing. It is increasing. It's not that it is steady, but that increase is slow. This is a classic figure which is truly physics. Exactly same as stud. This earlier figure is from stud. Okay, this figure is from stud. I marked it somewhere, but it is not able to see. Just mark it is stud. This figure is from a paper that I took, published in 2020. The reference is given there. This is the same thing they did for mid latitude. And you see, we may think that this is actually some fog or something like that going. Actually, no. What that fellow plotted is d theta by dz, altitude gradient of virtual potential temperature. All right. And you can see stable layer because where it is negative, positive, you have stable, unstable conditions. Correct. And the way in which the boundary layer get developed, and capping inversion, where the clouds get formed. The entrainment zone, there's a zone over which you have the stable atmosphere above and the convective atmosphere below. It is not that there's a single layer, surface. There's a layer over which the other fellow comes in here and then goes back. Okay, this is called entrainment zone. So the square root of the variance, that is actually turbulence, is shown in the bottom. The bottom is actually diurnal variation, the square root of the vertical velocity variance. It is nothing but caused by turbulence. You can see the daytime turbulence, nighttime residual layer. But you can see even in the bottom, there is still some finite amount of grayish color in the nighttime. It has come because of the wind shear. So wind shear plays a role in the surface layer getting mixed. So in the industry and all, what they will keep is, they will keep your emission towers, if there's a huge polluting industry, above that nocturnal, this plane, this particular evolution, it has to go above. So it is not that the towers in a polluted industry is kept just 2 meter, 5 meter kind of thing. It has to go above the nighttime highly stable layer. Otherwise, whatever you are emitting will simply come down and choke you, especially if it's a polluting industry. In the urban boundary layer, an entirely different thing happens. What is shown there is, top figure is for the daytime and the bottom figure is for the nighttime. And what is plotted, the XY graph is the potential temperature variation. You see, potential temperature initially decreases with height, means it is unstable. Remain constant, that is neutral. And then potential temperature start increasing. But let me tell you this, it started decreasing with height. It becomes unstable. Now it has pushed the air. Now the pushed air will go so long as it is pushed through the residual layer. Because as I beg your pardon, neutral layer, not residual layer, neutral layer. Because neutral layer, where you place it, it will go. So though the turbulence is there only in the lower atmosphere, the same turbulence will be going up to the top of the boundary layer, because residual layer will respond to the forcing. It's something like I will be standing here, like if you push me, I will go. If you don't push me, I will not go. So if you continuously push me, I will keep on going. But the moment you stop pushing, I will stop it. So that is the residual, neutral layer. So boundary layer will be getting developed up to that place where potential temperature increases with height. But you see, now you have, this is x-axis is the distance across a city. Okay, now you see buildings. And you see the potential temperature is increasing even up to higher height, means boundary layer height is slightly higher over the upper boundary layer. And that gray portion indicates that when wind is coming, it takes the pollution from the urban boundary layer in the downwind direction. See, such a simple figure, how much they showed. It will be pulled into the downwind direction. Okay, pushed into the downwind direction. And far in the downwind direction, your potential temperature now again becomes, the boundary layer height becomes slightly lower than the urban boundary layer. This is the daytime thing. Means over the daytime, you can have the urban boundary layer simply pushing, going high and pushing your pollution to very far off distance. In the night time, that is the beauty there. In the night time, it becomes surface in the other place where it starts become very stable. You see, potential temperature keep on increasing, so it is fully stable. But in the boundary layer over the urban thing, you see, IR heat trapping is there. So still there is convection that is generated because of the potential temperature decrease with height. It is unstable. It will push the boundary layer slightly to the upper. So that is why you can see that upper portion of that line, that horizontal line. Up to that it will be pushed, and then it is stable. So nighttime pollution will not go as high as the daytime pollution, but the beauty comes later. The city ends. Now the surface boundary layer at far off distance from the sea, from the city, is now clean. But just above that, there's a huge urban pollution that get transported. See this. This is the boundary layer effect in a city. This can be typically of the order of 300 meters, because nocturnal boundary layer height even in the city will not go beyond 300 meters. But if otherwise it will be maybe of the order of 100 meters in the background system, it can be of the order of 100 meters. But here, remember, they consider only theta. But turbulence also can be generated by wind shear. So where there is a wind shear, there can be still turbulence. But the urban pollution, you see, the urban plume can be still transported long distance through that stable layer far off from the city, but not right at the surface. See how important is the boundary layer, urban boundary layer impact. Now, urban island, heat island will produce so many other effects, like changing the precipitation pattern, clouds, all these things will get changed. Okay, we will not dwell much into that due to lack of time. One thing which we regularly face at Tumba or any coastal region is the sea breeze circulation. Sea breeze circulation means sea temperature doesn't change much, maybe 1 degree centigrade during the course of the day. But land get warmer, or daytime it get very warm, parcels start rising. And you see in this figure, you can see left side is sea or lake, right side is land, and huge convection takes place. Pressure get reduced. Air come from there, sea. It transports, and then boundary layer clouds get formed. And then it goes back, the same thing, and then sinks there. Because this air has come now, there has been continuity. So there will be sea breeze circulation. This fellow who generated this figure is an amazing person. You see the way in which he has kept the clouds. He kept the cloud very close to the coastal line, okay, into the land, and a little bit into the ocean, not far. And away from that, no clouds. I will show this at random, which I photographed. And in the night time, exactly opposite happens. Instead of sea breeze, it becomes land breeze, because land becomes very cold, the sea becomes, temperature did not change much, so it will be reverse flow. But difference is, sea breeze thickness will be very high. It can be up to maybe 600 meters or maybe even more than that. But land breeze thickness will be very shallow. It will be of the order of a few hundred meters, maybe 100 meters, maybe 200 meters, not beyond that. And land breeze effect is completely different from sea breeze effect. I will not dwell on the right side graph, although it is very interesting. This is about a sea breeze front that is going, but we are approaching time. This is what I photographed when I was coming in the morning, afternoon, not morning, pre-noon, Orthumba in an aircraft. You see, all the clouds are here, very close to the sea, and that border and beyond is sea. Absolutely no cloud well into the sea, but slightly in the fringes of the sea, you can see still there are clouds. So in that schematic, you see the fellow, he put it in 1987 for some other region. You see the depth, the size, frequency of that cloud. Exactly what you observe. We may think this is a feast for the eye. No, it has huge implication, in fact, for the surface dynamics, boundary layer dynamics, because these cumuliform clouds can modify boundary layer height, boundary layer energetics. We have studied this. We'll come to that. I will skip this. This is about Ekman spiral, and I will again skip it because of lack of time. And this we already discussed. Then there's a logarithmic profile which you can actually generate. Actually, aerodynamic roughness will come from here. So the velocity if you take, and there is something called a scaling in the boundary layer. So you always scale it with a standard parameter. For example, here it is scaled with the U star, which is called the friction velocity. It is actually stress term. Okay. And then for any place, if you normalize with respect to this, that right side equation is valid. And all what you have to do is Z0, which is the roughness length. Depending on the roughness length, your profile shape will change. That's what it means. And this is an example of roughness length change over different places where roughness length is different. For example, open country, woodland, and city center. Roughness changes, and you see the wind variation changes. Nothing else is changing there. You see the effect of surface length in terms of altitude variation of wind. It's a very important parameter. And of course, turbulence also. And when you see the total wind in the boundary layer, unless in the free troposphere or stratosphere, it is a combination of mean wind plus waves plus turbulence. And turbulence becomes a very important factor. That you can see the mean flow and then the waves, which are the main things in the free troposphere and even stratosphere paka. But in the lower atmosphere, you have the turbulence. And turbulence can be generated by the thermals, which we already told. It can also be generated by the wind shear, and it can be a deflected flow from an obstacle like a mountain and things like that. And there is something called the Taylor hypothesis. The Taylor hypothesis is you have an eddy. This eddy is assumed to be preserving its shape, and it will not. That eddy as such get advected, which means if I make a measurement at a point, it is as though the eddy has traversed through you and you are seeing different portions of that eddy. But actually what happened, this eddy has moved. But without Taylor's hypothesis, you cannot do any measurement of the flux that we are making, because we assume that the same eddy, it preserved its shape and then moved, which is a valid assumption because the time interval which you are keeping is of the order of seconds, or maybe the order of even a few minutes, that's all. So Taylor hypothesis will be valid, but we have to know that it is under the assumption of Taylor hypothesis that the eddy preserved its shape within that time interval over your place that you are able to do further analysis. And we keep, at different layers, and it has to be away from obstructions, because one of the things is you cannot keep a boundary layer observatory at any place where you want, because we said that the roughness will affect. So if I keep my observatory just across this building, I'm not going to measure anything which is related to the boundary layer, but it's completely damaged by this. I need at least a large area. Ideally speaking, if I have a 30-meter tower, I should have full open area 6 times larger than that, and keep it away, at least 6 times away from that. Still it will be affected, but it will not be much affected for 30 meters. Lower ones can still be affected. This is one of the problems. Getting such an open area is one of the problems in boundary layer dynamics. Other aerosols you can keep anyway. So that is the advantage of aerosol, but boundary layer you cannot do that.
Sensors, they used to tell like that 1 kilometer radius.
1 kilometer. Actually, that is the ideal thing. Like, for example, a forest you keep pakka. But ideally speaking, even if you want to make a representative measurement, because you cannot have 1 kilometer homogeneous thing in the urban area and things like that. So the best technique that you can do is eddy covariance system, which will give you turbulence, surface energy balance, water vapor balance. Of course, it gives you additionally carbon dioxide fluxes, just huge other impacts in terms of climate and things. I'll not go into the details except that this basically contains a sonic anemometer which can measure three-dimensional wind at typically 20 hertz. It can be even 30 hertz, 40 hertz. It can be 10 hertz also. Also, it is 10 samples per second. It can generate turbulence. It can measure turbulence. That's what it is intended. And three-dimensional, both the U, V, W, all are required. And there is another parameter called T. They will not say T, T prime. Okay. So it is actually sonic temperature. It is at the speed with which the sound is traveling. Sonic temperature. The second thing is very close to that. Very close to that, they will keep a carbon dioxide water vapor analyzer, an open path system, through which air will be sucked in and then air will be going out. And they will continuously measure water vapor in that at the same frequency as the sonic anemometer. Now you see, you are getting a time variation of highly varying water vapor and three-dimensional wind. You take out the mean portion of that, you take only the fluctuations. Now I am taking an example. U minus U bar becomes U prime. So U prime is the fluctuating zonal. Same is the case with water vapor. Q bar, there's no point in taking 10 unit. Actually, you see how much is the variability, Q prime. And you find out Q prime into U prime, or Q prime into W prime, or Q prime into V prime, depending on zonal advection or vertical advection. Usually, vertical advection is U prime, W prime, Q prime, W prime. And then average it over time. That much is the flux that is transported across. Okay. This is an important thing which we can debate further on. This is a typical example of how it is measured. And this is the earlier days we don't have these kind of instruments. It was in this recorder, the paper recorder. But they were making fantastic measurements with the paper recorder. See, all the insights what we get today is from that. And I told you about the genesis of turbulence. It can be generated by thermal, mechanical processes, wind shear and things like that. And to quantify turbulence, we have a number called the Richardson number. Richardson number is, d theta by dz. That is whether it is stable or unstable. And below is the wind shear. So denominator is the wind shear, upper region is the stability. So stability by wind shear will give you Richardson number. And if Richardson number is less than 0, it is thermally unstable. Because d theta by dz is negative. But d theta by dz can be positive, but still it can be unstable from wind shear if Richardson number is less than 0.25. If Richardson number is more than 0.25, there is a tendency for stable. See, I did not write that it is stable. I wrote there is a tendency for stable. Absolute, you cannot say that 0.5 is not stable. Ideally speaking, in the free atmosphere, even up to 1, Richardson number 1, it can be stable. Bulk Richardson number, even up to 1. But beyond that, it becomes stable. Up to that, there's a possibility that it can be unstable. So that's why I used tendency for stable. You have to use your words correctly, because otherwise it can be a misthing that beyond 0.26 stable. Sorry, it is not so. And if I take the spectrum of movement, you have sonic anemometer, you have 1 day of analysis or 10 days of analysis, you simply do a Fourier spectrum in terms of analysis. You'll find that there are 2 peaks that come. One is a large scale process that is associated with, for example, you have 5-day variations, 10-day variations, or waves advecting or monsoon activity and things like that. And on the right side, there will be another peak that is coming. That is associated with turbulence and then decay of energy. The peak and the left, that small portion, is called the place where it is getting generated. That is the largest eddy. Energy is getting generated. And that eddy is now getting decayed, because a big eddy will lead to a smaller eddy. You just put, a big eddy, that big eddy will not go like this. It will produce shears within that. It will produce a smaller eddy. That smaller eddy will produce still smaller eddy. And then it will be cascading. That's why there is a decrease. And the decrease is not just simple. The decrease comes like this. But let me tell you, I forgot to tell. The y-axis is the relative spectral intensity. X-axis is the frequency. Frequency or period. Both are put there. Okay. It's taken from start. So this is a variation. I just expanded on the right side of this for this turbulence. You see, this is the input of energy for the largest scale. That is the largest eddy. And from there, there's a slope that it always follows. That is called inertial subrange. Always, if the y-axis is energy density, and x-axis is scale size, which can be the number when you do Fourier analysis, you always will get the same slope. It is called inertial subrange. If you don't get this slope as minus 5/3, it means there is another additional source that is existing, or there is additional dissipating parameters. This is for a saturated spectrum. A saturated spectrum means a larger eddy leads to a smaller eddy, that further leads to the still smaller eddies and still smaller eddies. So bigger eddy, that feeds to a smaller eddy, that feeds to a still smaller eddy. That means energy has to be conserved. If energy has to be conserved, then its slope has to be minus 5 by 3. Area under the curve may go back. For example, area under the curve can be smaller or it can be larger, which means turbulent kinetic energy can be larger or smaller, but the slope will be preserved. This is very important concept in bound layer. When you are talking about turbulent kinetic energy, this becomes very important. And beyond a scale size, turbulence cannot generate anything. It goes to the molecular diffusion level, viscous diffusion level. So that's why that slope becomes bigger. The region between where the slope is remaining minus 5 by 3 is called inertial subrange, which means a larger eddy leads to smaller eddy, and it is called cascading. And you know Richardson, famous Richardson, who used the computer for the first time, the computer. And then he's the turbulence, Richardson number. He gave a poem of that. Big worlds have little worlds, which feed on their velocity, and little worlds have lesser worlds, and so to viscosity, till viscosity. See how poetically, but every minuscule thing is there. This we have already discussed. And identification of the bound layer is, you have to take where potential temperature remain constant or start increasing. That is the bound layer height. Potential temperature start increasing beyond that. That is the bound layer height. The bottom portion may have instability, small instability, which may be remaining may be neutral, but the top of that layer is the bound layer height. So you can get it from potential temperature. You can get it from specific humidity. Both of them should mutually they should. Then only you can say that is indeed suppressed. If you take only one of them, there can be other problem issues. And remember, T cannot actually give you that. If you take simply temperature, it cannot be. It will give a kink, but you have to be very, very careful. That's why you have to follow potential temperature to follow that. And ideally, virtual potential temperature, not the potential. The virtual potential temperature can change still slightly. And this is what there's a fundamental difference between bound layer height and mixing layer height. People often mistakenly use as the same. No. Mixing layer height is different from bound layer height. Bound layer height is actually thermodynamic bound layer height. Thermodynamic bound layer height means the place up to which a hot parcel from the lower atmosphere can reach. That is thermodynamic bound layer height. Above that, you have the potential temperature increasing. The mixing height, actually, even before reaching the top place itself, it can get retarded. There is another way speaking, if it is getting accelerated, it can overshoot the bound layer height because potential temperature it becomes stable. But I have a huge surfing that is coming from the bottom. It will penetrate maybe a few tens of meters, maybe 100 meters. So mixing layer height and bound layer height are different. They are not the same. Usually, the mixed layer height will be smaller than the bound layer height. Usually, because I told about huge convection coming and then overshooting and all those things which rarely take place. They will be slowly getting decelerated rather. So thermodynamic bound layer height will be slightly above the bound layer. You have to keep all these things in mind when you are doing analysis from. And there is one more thing. Solar bound layer height will be still different because solar generates turbulence. Solar is detecting turbulence. So where turbulence is maximum is the place where solar or radar also can detect bound layer depending on the place where your turbulence is high. Your return back single strength will be SNR. So, but they will not be exactly same. There's a paper, Mahat. He defined these three things. That paper contains only this. The difference between turbulent bound layer, thermodynamic bound layer, and mixing layer. Okay. We have to know these things. These pictures are all telling about that. This is actually over a hilly terrain. You are telling about hilly terrain. Over a hilly terrain, this was over Shillong. We had IGBP Noble, we had a project. And we have a project even now. And this is from Shillong, NESAC. You can see the bound layer, the right side shows the solar bound layer height going up from the SNR. That daytime it goes up, it means the turbulence is going up. This bound layer height is going up. And remember, this is already 1 kilometer above the ground. And above that it goes another 600 meter or 700 meter. Okay, whereas around 30, 40, 50 kilometer down, you reach Guwahati. Now you see, Guwahati bound layer height is 1 kilometer. Shillong is above Guwahati. Shillong itself is 1 kilometer. well above the boundary layer height of Guwahati, and it develops another boundary layer above that. So you see, within around 60 kilometers in a mountain terrain, how the boundary layer changes, boundary layer height changes, and in turn, you know, there will be orographic circulation. There will be katabatic wind, anabatic wind, which can take it aloft and then come and sink in the stable layer of the boundary layer over this place. And let us renew this. What is the thing? There is no closing. Right. Do you want to allow this app? No. There is no. Okay. So, and not only that, the corresponding changes in wind. This is actually left side is showing the vertical wind. You see the vertical wind, the thermals are getting generated in the daytime and then going up to thermals. This is something which we did from the LiDAR. And I would like to, instead of going into all these, you can see the development of boundary layer, which you conventionally see from a LiDAR, that is from the backscattered aerosol mixing. Actually, it is mixing layer, right? But we had a dual polarization LiDAR. This is the bottom graph shows what is the polarization difference. Okay, and you see, though you see there's a spike that is going, which is what you would have identified from a conventional LiDAR. That inside blue portion you see, that has distinctly different depolarization, means distinctly different type of aerosols, because that is coming from the sea breeze and it has much more, humid and stable. Pristine coming compared to the polluted and the single scattering albedo, not scattering, single scattering albedo. Here, what it matters is a non-sphericity, because it is depolarization, non-spherical, but in the night time reverse happens, so it comes and mixes. So depending on your instrument, you can study this and then go into the details, and you can study with a single place. You can study the structure and evolution of the boundary with a simple LiDAR. And this is one thing which I would like to stress upon. You have a lot of scope because you have an MRP here, I understand. MRP versus radius on a comparison is made by Edwin's work. And of course, Renju also did very similar work, mentioned here. They are reliable, but not that exactly within 1 kilo-Kelvin or within 0.5 Kelvin they will agree, but they are somewhat reliable for the large scale dynamics. And this is how Edwin derived the boundary layer height from the virtual potential temperature parcel method. That parcel method is at this particular time, this much is the parcel potential temperature. What is the potential temperature of the atmosphere at which this becomes equal? So that is the boundary layer height. You can see a very clear diagonal evolution of boundary layer going up to around 1 kilometer. And remember, this fellow is not able to detect the internal boundary layer. Actually, there would have been a small change which take place at around 300, 400, 500 meter, which is not happening because of the resolution problem or smoothing of the, because it is coming from an emission function. It cannot have a rapid change. And he compared it with the ERA 5, it is agreeing on a larger scale, but it doesn't agree on a day-to-day scale. Okay, that is the bottom portion. And this is how this is the advantage, this is the power of that. You can have it every day when there is cloud, when there is no cloud, except when there is precipitation, you can derive the boundary layer characteristics, boundary layer height, and all those things continuously. That middle portion, that XY graph shows boundary layer height is a continuous evolution. Okay. And with that, now you can come to a solid conclusion with the multi-year observations. What it is, x-axis is the local time, y-axis is the month, and it shows an annual cycle of the boundary layer, annual diagonal cycle of the boundary layer, that top left image shows annual diagonal cycle of the boundary layer. But let me tell you as a precaution, the bottom portion says it is less than around 100 meter, around maybe 100 meter or so. But it need not be, because this is only coming from the thermal property. There can be wind shear induced turbulence, and boundary layer height can be slightly different in the night time. But daytime it is going to be the same. So night time anyway, there can be variability of the order of 100 meter. Now he has done it for seasonal variation of this, which shows that during the pre-monsoon season and the winter season, you have the largest boundary layer height. Summer season, you have low, summer monsoon season. The reason is summer monsoon, it is relatively cool here, and then more soil moisture here. Surface temperature doesn't enhance drastically. Whereas winter time it is very high, because absolutely clear sky. We may think that, because especially that winter is here, this, winter in the tropics doesn't mean it is really winter, especially in the equatorial region. There's no winter. You only classify it as winter. So, but what I want you to see here is the rapid development boundary layer between around 8 o'clock up to around 10 o'clock. And subsequently, it just falls. But it falls only because at Tumba. Suppose I was making in a continental region, same thing would have taken place, but that enhancement and peak would have come at around 2 o'clock or 3 o'clock. Because here, by the time around 10 o'clock or around that, sea breeze starts setting in. So you have a developing thing, but the sea breeze supply a small break. So your convection level will be retarded. So you will not be able to go further up, especially after strengthening of the sea breeze. This right side I really like. This is the impact of clouds on bound layer height. For the same season, for winter, you see the top, top left of that foregraph. Black is when sky is absolutely clear, and red is when overcast clouds occur. Bound layer height becomes entirely different. Why? Because clouds get generated by the bound layer processes, or can be from, I would say, like for example, advected clouds. But that cools the surface. The thermals are not able to go up because thermal doesn't have that much energy in it. So bound layer height becomes completely different. And in fact, it becomes half of that. So this is a problem in bound layer. If this happens, the moment the cloud gets developed, bound layer height can come down. And if it lasts for a few hours, like 1 or 2 hours, bound layer height can be significantly lower. Now, how do your model take care of that? Is the question. That's the problem. That's why Terra is not able to exactly reproduce a local phenomena which is taking place. Local doesn't mean that it is Tumba. It would be the case when you take about the coastal region in the Southeast Arabian Sea. It's a representative. So with this, I will stop. I am very sorry that I took a little bit more time, but the initial portion of the thing, the bound layer portion took only, ideally speaking, 1 hour. But the initial portion, we spent much more time. I was seeing it is almost started at 12 o'clock. Okay, but it's very important. This graph is not just an image, but it shows the trapping of the bound layer. Aerosols below the bound layer, but I will not call it as a bound layer. It is symptomatically, it's a bound layer. It can be trade wind inversion also. But here I am telling bound layer because you can see the bound layer clouds and just spiking above the bound layer. So you can have the trapping of the aerosols. This happens especially over places like Bombay and highly polluted areas where you are going in an aircraft, you look down, you will find that there's a huge chunk of bird curry kind of thing. And above that it is clear. Below that it is not only just Bombay, any polluted place you can see where Calcutta when you are coming on flight, when you are coming down, you find these kind of Trivandrum and all you may not see it much, but still you will see. There's some amount you can see. And when you are going to pristine area, you will not see this at all. It becomes absolutely. So this shows how much bound layer will be affecting the pollution dispersal even locally. Anyway, so here I will stop. If you have any questions, I can answer, or we can have discussions. But I will stop the presentation. We can stop the video under somebody else any question. Or
Which factor will influence the boundary layer? Like we're talking about the mixing and transport.
The most important parameter for the bound layer will be the surface energetics. Surface energetics is largely controlled by the surface temperature. Surface temperature is mainly controlled by the solar radiation that is.